here's an example. So we have a pendulum, a rigid body pendulum. Okay, so that's a rigid body. That's the pivot O, and let's say this point is P, and it's got the center of mass G halfway between O and P. So let's say that distance is L. That distance is L over 2, okay? And then let's say some mass strikes the rigid body, okay? Okay, so a rigid body pendulum which is a uniform bar of length L and mass M2 hangs from O as shown. Another point mass by point mass we mean particle as opposed to a rigid body. M1 collides with the pendulum. Exactly hitting G, the center of mass. Okay, G on the pendulum. It is a plastic collision. Which means that the two masses move together after the collision. Or stuck together. / move together. After the collision. Okay. The question is, well, let's give a couple of more pieces of information. M1 is traveling. Horizontally with speed v just before the collision. Question: what is the angular velocity of the new object composed of M1 and M2? angular velocity of the object pendulum plus m1 just after the collision. Okay, so that's a question. So solution. So if you take, this is not quite a rigid body, it's not quite a free body diagram, but during the collision, we have basically a big force between the mass and the pendulum during collision. So if you want to draw a true free body diagram, looks like this. So we have this rigid body. I guess I meant to draw this twice as long. So we have this mass. On this mass is a big force, and on this pendulum there's a big force, equal and opposite big force, and this is the force of interaction between the little mass and the right? And then there are these reaction forces. And it turns out the reaction forces might also be big because, well, so these are big interaction forces. Let's just write them down. These reaction forces at O can also be large. When we say big, we mean infinite in the limit, right? Can also be infinite. Because think about what the role of a reaction force is. A reaction force is what is keeping that point O fixed there, right, in some sense. If it were not for the reaction force, this point would start moving. It's a reaction force that's keeping that point there. And in this case, if there's a big collision involving this mass and this mass, the reaction force is responsible for essentially opposing this force in the general sense, in a manner that this point does not move. So the reaction forces can also be so-called infinite in the limit where these forces are also infinite. Okay, so for the system as a whole, the reaction forces can be infinite, and then there are internal forces between this mass and this mass that are infinite. So what should we do? We can do linear momentum balance, we can do angular momentum balance. We can do angular momentum balance for just this mass, or just this mass, or the system as a whole. What we are going to do is do angular momentum balance for the system as a whole. So notice that I've not drawn the smaller forces like mg, mass times gravity, because those forces do not really play a role in collisional mechanics. Okay, it's only these interaction forces that play a role in collisional mechanics. You can sort of ignore gravity. Ignore finite forces like gravity. In any case, what we're going to do is essentially take moments about O for the whole system, okay? Angular momentum of the whole system is conserved across the collision about point O. Right? So, and that's because, well, if you consider the whole system, the only forces on only potentially large forces are Rx and Ry, and the force between mass m1 and m2 is an internal force, so it does not appear on the free body diagram. In fact, you can even add gravity if you want, but those also don't matter because, well, A, they are small, B, they are actually passing through point O. Okay. Okay, so we're taking moments about point O. So we're saying the only potentially large forces pass through O. In any case, so let's do angular momentum about O before equals angular momentum after. H about O, H is angular momentum, initial equals what? This is now going to be H O I of M1 plus H O, H with respect to O, initial of M2. Okay. This, of course, is just 0. This quantity is just 0. So, and then this quantity is basically velocity, R cross mv is basically the formula for a particle. R, g with respect to O, crossed with mv, the velocity of the mass m1, I, that's the velocity before collision. Okay, and then this quantity is just 0 because the pendulum is just hanging downward at rest. Okay, so we can write that down. This is Rg with respect to O is going to be minus L over 2J. Okay. G with respect to O, that's G. G with respect to O is minus L over 2J. Okay. Crossed with MVI. That's going to be equal to MVL over 2, negative J cross I. J cross I is minus K, negative J cross I is going to be K. Okay, so that's the initial angular momentum. So just to summarize, that's the initial angular momentum about O. Okay, let's call that equation 1. Now, what's the final angular momentum about O? Final angular momentum about O is now going to be the angular momentum of, again, this particle moving, translating, and then also this pendulum rotating, and then it's now rotating with an instantaneous center of rotation O. Okay, so let's write those things down. H about O final is still R G with respect to O crossed with M, the velocity of 1 final, right, plus this is of mass M1, right? And this one, again, I should have said M1 here. M1, 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 M1. M1, okay? So that's of mass M1. And then the moment of inertia of the pendulum is going to be, let's say the final angular velocity is omega final. It's just going to be I-O omega final K, okay? So because pendulum rotates with instantaneous center of rotation O. Okay, so what is V1F? V1F, which is the final velocity of this mass, is going to be, well, because it's stuck to this pendulum, its velocity is going to be the same as the velocity of point G, which is going to be L over 2 times omega final, okay? That's the velocity of G, and then that's in the I direction. So we can plug everything in. What is I/O? I/O is using the parallel axis theorem, Ig plus M L over 2 square, right? So where this thing is OG square. And you can either derive this or you can remember this, or we will give you it. So Ig is ml squared by 12 for a uniform bar, which is something that we will give. This is ml squared by 4. And if you do the simplification, you will get ml squared by 3, okay? So that's I sub O. Okay, so let's plug all that in to here. So let's call this equation 2, 3, 4. Use 3 and 4 and 2. So H about O final is minus L over 2J crossed with M L over 2 omega F I. That's basically this quantity plugged in, plus ml squared by 3 omega F K. Let's simplify this a little bit. You're going to get L over 2 square, L over 2 whole square M. So just to be clear, this is M1. this thing is going to be m2. This is of the okay, so all this is m2. Okay, so let's simplify this further. So m1 L squared by 4. J cross I is k. J cross I is k. But then there's a J cross I is minus k. Sorry, J cross I is minus k. There's another minus sign which gives you a plus k. So okay, so that's what we get. We get L square m1 by 4 plus m2 by 3 omega f k. There's omega f missing here. Okay, so again, what we do is total angular momentum initial equals total angular momentum about O final. So let's call this 5. So basically, we are saying 1 equals 5. Let's write the right-hand side. L square m1 by 4 plus m2 by 3 omega fk, and then 1 is mvl by 2. Okay, and then that's it. We can cancel an L. Cancel an L. I suppose this was m1, just like this was m1. And that's it really. So you can cancel the k's as well, because it's not that we are dividing by k. What we're doing is equating the components along the k direction. So what we have is omega f equals mv divided by 2l. This is m1v, m1 by 4 plus m2 by 3. And that's the final angular velocity of the whole system. And that's the answer.